Oh my goodness, I am so excited that today you have not, hold on, let me turn the music on. You have not one, but you have two AI show hosts together for the first time since, I mean, when have we done a show together? It's been a while, right?
It's been a while. I mean, I come and heckle you sometimes in the chat,
Mm,
but
I do the same for you. You were
yeah.
telling me that you were working on a really cool project, and I was like, I would love to get into the bowels of the project and see if I can
Mhm.
understand what you've done. Why don't you tell us what you've been doing?
Yeah, so obviously large models are kind of taking over right now, and they've been really really big breakthroughs, I think, really in the last 2 years. And one of those is around text to image generation.
Uh-huh.
So yeah, and so I've been playing around with the Stable Diffusion implementation of a text image generation.
And we had a show a
However,
couple days back with, well, a couple weeks back with Vlad, who did Stable
yeah,
Diffusion, right?
yeah. So I was thinking, what if I could do this in C sharp and run it locally on my machine? Because as you know, these models take a lot of power to run. They're generally written in Python, right? And so this is very much something that I've been working on to see, is it possible, and what could I actually create? So to
So
do
if
that,
the
I
lights
had
start
to start.
flickering, if the lights start flickering in your house, we know it's because you're running Stable Diffusion.
Yeah, yeah, no, that'll probably happen at some point. If my video cuts out, it's because all my resources locally are going to the AI.
So for those that don't know what Stable Diffusion is,
Mhm.
can you let me know what that is?
Yeah, so Stable Diffusion is I give you a text prompt, or I give the model a text prompt, and it creates an image based on that prompt. And you can even ask it for multiple images. So let's say you want, a picture of a cat with a mask riding on a horse with a Microsoft flag. Maybe that's something that you'd be interested. You could give it that prompt and say I want 3 different versions or even just one version, and it'll go through and it'll actually create an image based on your text prompt, which is just so cool.
Yeah, I mean, I'm not very artistic, but I can write a mean sentence, and so hopefully that would help me fake my artisticness, so to speak. So, like, give us a sense. Like, can you walk us through like what the process is for doing something with these models, and then let's dive into some code. What do you think?
Yeah. So I'll pull apart how these models are working. There are really like cool libraries which will look at like diffusers, which make it really easy for you to just grab pipelines and play around with them that have implemented the models for you. We're going to implement each step manually so we can
Ooh,
kind of pull it apart and see how it works. Some of the
ooh.
use cases that I like think about for this is if you as a creative, even I could see them using it as an inspiration. Like I think of AI, and even with the text models, they're there to help you, and things are better with human plus AI. Like AI is cool and it can do all these things, but it's still not human, right? We're still smarter. I promise. And so I think
Some of us.
the what's that?
Some of us are smarter. Maybe this way. Some of us are smarter, right?
So I
But
think it's cool to think about
But
it.
I want
Like,
to ask you something before you
yeah,
get
yeah.
before you get. So, if I understand this right, we're going to be going step by step how to run the diffuser model, but in C sharp, which is not traditionally how it's done. What's the magic there?
Well, so there's multiple models in this, and we'll pull it apart. But there isn't a C sharp library currently that would allow you to just go, hey, I want to run diffusers without doing all of this work that I've already done. You can run the models with ONNX Runtime. So we're going to be using ONNX Runtime in order to run the different ONNX models, get our inference. But there's a lot of processing and different things that need to happen, and a lot of math that needs to happen, which we'll look at in order to get a good result. There's a lot of tensor manipulation. There's a lot of different things that you got to do in order to get a model to work in C sharp or in any language. It's just in Python, Hugging Face and diffusers already did all that hard work for you. So,
Mm. So you said math, and all I thought was. So
your
anytime you say
favorite.
the word math, I gotta push the air horn there because I love math almost as much as Oprah loves bread. Do you remember those commercials? She's
I
like,
have not. I've
I
not seen
love.
those, but I mean,
Look
like,
it
I
up.
think most people love bread, right? It's just,
I love. No, it was like some diet bread or something, and she was like,
oh,
I love bread. And I was like, that's how I feel about math. It's great.
You should have a T-shirt that just says "I heart math." Do you have
Yeah,
one?
I mean, I should have worn it today if I would have known. I have my air horn ready though, so anytime you say here's some math, I can just push the button here. All right, so what do you got to show us?
All right, let's jump into this demo. There's a lot to go over. So, it started with this blog from Hugging Face for the diffusers library, and one of the ways that I like to learn and figure things out is reverse engineer them. So I took this blog and I looked at what they did and I started pulling it apart. So I'll provide this blog. It's an amazing blog with tons of good resources for anyone that wants to start pulling apart how Stable Diffusion works.
Nice.
And it's around their how they did their diffusers library, which has an ONNX Runtime pipeline as well. It has multiple different pipelines, different versions of models. So if you want to run in Python, that is the way to do it.
And people don't know this, but you maybe they do. You are on the ONNX Runtime team, PM
yes.
team. Yeah.
Yeah,
So
exactly.
okay. So that's why I was like, ooh, this is your stuff.
Yeah, it is. There's a pipeline. So if you saw here when you create the different pipeline with the diffusers library, there's an ONNX pipeline as well that you can use.
Delightful.
So let me scroll down to where it starts pulling it apart. But here, I guess, is a good example of, you saw the prompt of, what was it, a photograph of an astronaut riding a horse. And then you can see the different versions and how good quality they come together. I mean, there's still some pieces of it that are like that's a little creepy, right? There's still improvements to be made.
Look at the foot, though. The foot. Let's do a zoom in on the foot.
Yeah, the foot too. Look
it
at
looks
that.
like what is that?
It looks like a stuffed animal foot, kind of, doesn't it? Like a teddy bear.
Santa foot or something. There's no ankle or like what? How do you say what's the back side of your foot? What is that called?
Achilles heel.
The heel.
No,
Yeah, that's it. I'm so
heel.
like
Okay.
Yeah, the heel. Like I said, some people are smarter than others in this particular meeting, and it's not me. Oh,
the other thing that I think is kind of weird on these models is look at the fingers. Also, I mean, we could assume that maybe his foot is underneath the horse.
Maybe it's an alien disguised as a human on a horse on a secret mission to take us over.
Oh my gosh, it kind of looks like an alien. Look, there's an eye. There's an eye.
Sorry, I was late on that sound effect. I was supposed to say maybe it's an alien. Okay.
So this one.
Oh, yeah, that one.
Yeah. So it's still really cool that it's able to create these, but humans are still better at creating images. But I think of it as your creative sidekick.
Yeah.
It could get you started and then you could go from there.
I love this idea of responsible co-creation with these models, right? Because the blank page problem is a real thing. Like when we're having our ADHD moment and we're like, I have this task that's literally going to take 15 minutes if I sit down and do it, but instead it takes 8 hours and I get it done in the last 15 minutes of the day. I mean, maybe this could help us undo some of that damage.
Yeah. I really do think it can. And I think it can help us with some of those also just kind of monotonous tasks that can be automated that are easier. I think the same thing with Copilot. I play a lot with Copilot and different code generation and with the ChatGPT and the Bing chat and all of that stuff, seeing, what can it do? And it's really helpful, but it still needs a human. They're just really good book around human plus AI. And it kind of goes into that and those different sci-fi scenarios based on current science of how these things work better together and why we need both. And I think that's kind of the way we should start thinking about it. That in truth, I mean, people will be more productive. So maybe you would need less people to do a particular thing, but you still need a human that understands it in order to create it.
Is that a book or is that like a blog post?
It is a book.
We're going to Google with Bing real quick.
Yeah. Human plus machine. That's what it is.
Oh,
look at chat. Wait, what is it called? Bing chat, right?
Ooh, it's looking for look at that.
So it actually knew that this was the book I was looking for.
Ooh, yeah, you just literally, whilst you were explaining the book that's going to explain to me
Yeah.
how we can do these things together. The AI help me help you explain it to me. Did I get
Mhm. Should we ask it to tell me more about it?
yeah,
This is so
tell me.
cool.
I didn't you have access to this already? I must not be as important.
I got access at like 10 p.m. last night while I was working on Stable Diffusion. I shouldn't actually admit I was working that late last night. I'm really excited about this project.
we're I I was me and Cassie are like literally the same person. I stayed up till like 2 last weekend building
Rude.
my own
You know,
GPT
when you're
style thing.
excited about things, it's
Mm.
hard to stop. That's for my thing. So, like, when I'm really excited about a project, it's really hard for me um, to stop and work on something else. And so, since I've been working through the scheduler bugs,
Human
which we
process.
might get to that piece of it, it's been really cool and really exciting and really hard to put down. Kind of like a good book, I guess, or any or a
Yeah,
puzzle or something like that.
indeed. I'm gonna you so you read this book and you said it's good, right?
I am about like a fourth of the way through it, and I do like it because it talks about, like, socioeconomical things, it takes into, like, a lot of current world issues and then puts them in this fictional state, but then applies how yeah, so it's a really interesting mixture like, truth, fiction, AI, sci-fi, like, all of
Mm.
these different things kinda come together.
And
Um,
guess what, Cassie?
yeah,
I have 5 credits in Audible that I have not used. I am getting an Audible. I am gonna listen to it, and next
yeah,
time you can quiz me on it. Purchasing now.
awesome. Okay, so let's go back to our
Let's do it.
Stable
The thing,
Diffusion,
we had a
right?
little ADHD moment. That's okay, though.
Yeah, that's what happens when we're
That's
live-ish.
right.
So there's a lot of different pieces that go together and a lot of different models that come together. And I think a lot of the really interesting and powerful things are becoming multi-model solutions where you have multiple models to create one solution. Where I think a lot of it before we were thinking about it as one model. So I love this diagram here because it puts everything together. So you start with a noisy image. So it's just like think about like static, like if you ever had a tube TV, if you're old
Yep.
like us, you had a static TV, and you had to go through with the turn to find the right channel. That was basically analog stable diffusion, right? No, I'm just
Ooh,
kidding.
yeah.
So we're turning the knob. The scheduler keeps turning the knob until it gets a good image, based which we'll get into. So we have this noisy image, which creates our one of the inputs for our UNet model. And then we have our prompt. So we were looking at the example of an astronaut riding a horse. From there, we need to tokenize our text. So if you've done any BERT or any natural language processing, you're familiar with the tokenizing process, which
Right.
I think simply put, it takes words and maps them to numbers. And then from there, we are getting a text embedding,
Uh-huh.
and that is one of the other inputs to our UNet model.
What's the
So the
dictionary
UNet
size on
model
this? Sorry, what's the dictionary size for the like, how many
for the
words can it use?
tokenizer,
Yeah,
uh, that is a good question.
because I
I
always
think that
wondered about that, like, how many how many words can like, will it like, if it's a word
yeah.
because and this is I mean, maybe we'll look this up later, but, like, the amount of words is fairly constrained, like, I think even the biggest models have, like, 50,000 words or tokens or something, right?
Yeah. So, like, how many words is it actually in
Oh,
oh, look at that.
see? How close was I? 50,000. Boom! I had, like,
Yeah,
latent knowledge I had no idea I had. This is glorious.
that was impressive. I'm just gonna start we should call it Chat Seth, you
Just
know?
yeah, just call me up and, it's basically there was a I don't know, there was a funny video I saw on LinkedIn where, like, ChatGPT was just some dude, like, randomly answering questions, like, somewhere far away. It was so funny, but
There's been a lot of cool implementations of it and just, like, seeing what's possible. We are just, I think, on the brink of actually seeing it become what it could be. Like GPT-3, the groundbreaking model came out in 2021, didn't it? And then this is all just building on that and fine-tuning it for different tasks. So, I think it's just really cool to see.
all I was saying is that these GPT models are just changing in structure, which is meaning size, and then the
Yeah.
data they're training on. These things are gonna get more specialized and do really cool stuff, right? I'm pretty excited.
Yeah, me too.
All right.
Okay, so we have our tokenization and we get our text embedding. And then we have our noisy image that we start with. And then what happens, and maybe you've seen some of these GIFs online, but it starts getting clearer with every step. So I tell it to do however many steps. The more steps I do, the clearer the image. The scheduler kind of like reconstructs the image based on the input or the output of the model and the previous image. And then it goes back through and it goes again until I have reached the number of steps that I would like to denoise. Once you have that denoise output, you use another model, which is the decoder. And the decoder is what changes the output into an image. And then you use that to then actually print out the image. So like at a high level, you're talking, so my tokenizer is also an ONNX model because I'm using ONNX Runtime extensions
I see.
that allows me to get this clip tokenizer in C# because it doesn't exist in C#.
Cool.
Yeah, which
Like
I'll show you how that.
this is groundbreaking. This is like we're like literal the royal we are breaking ground on some new code in C#, which is kind of cool.
It is. And the other cool thing about ONNX Runtime extensions and the clip tokenizer, it's for any language that ONNX Runtime supports. So there is, you can use it in Python, you can use it in JavaScript, you can use it in C#, Java, you can use it for iOS,
The
Android.
PDF of models, ONNX.
Right.
Like we could make like a we should make like a ONNX, the PDF of models. Purchase yours today for free at github.com. That was amazing.
That was really
Sold.
good.
Sold. Okay.
Okay. So I'm using that text to create my clip tokenizer so that I can actually tokenize it in C#. And then the text embedding is a model that's included that you can grab from Hugging Face. So the ONNX models I'm using are all on Hugging Face, and you can go and download the models if you just look for their Stable Diffusion models. Here you can see all the different ones available and kind of pick whichever one you'd like to use.
Cool beans.
Okay, so that's the high level of what is happening. And if you think about it, we have a model for our tokenizer, we have a model for our embedding, we have the unit model, and then we have our decoder model. And the other model that's not shown in here, which is an important part of it, is the safety checker. So before you output this image, you do a safety check here to make sure that there isn't anything that you wouldn't want to display in an image. So
yeah. How do you safety check it though? Like, is it like an eyeball test? Like,
it's
no,
a model.
that's not a good one. Wait, it does it? How does it?
Yeah, there's a safety checking model that checks for inappropriate images or inappropriate or unethical depictions, and it won't return the image if it comes back as unethical.
So that's when you say multi-model, you really mean like there's like 3 or 4 models working together to do the right thing.
Yep.
Are they trained at the same time? Like, is it like forward passing and then backward passing?
So I haven't trained it. I've only used the open source ones.
Okay.
That I'm not 100% sure. But yeah, I believe that. So for the clip tokenizer, obviously that's one just from our ONNX Runtime extensions library. The text embedding one, that is one that exists for the clip model. So there's a clip model, which is another image model here, that this tokenizer and embedding is for a different image model.
I see.
So like a computer vision model. So that one's separate. That's not part of the training of the UNet. As I speak about this, I think I could probably deduce so the tokenization embedding, that's separate, right? The safety checker, I believe, has been trained separate. It's just one that has been trained to find inappropriate images from an image, because your output is an image and it's checking from that image if it's okay or not. It just returns true or false.
Right.
And then the UNet model in the encoder and the decoder. So for inferencing, we're only using the decoder. For training, you use the encoder and the decoder. Those 3 models are specific to Stable Diffusion.
Got it. Okay. Cool beans. That makes sense.
So I hope that kind of answers your question.
Sure does.
Okay, good. All right. And now I read this blog and I've been playing with it and pulling it apart. So this is everything that I've just kind of figured out as I've gone based on the initial understanding that I've gained from this amazing blog. You know what? Let me go back up here for a second. Can we just give these people a round of applause for this amazing content?
Absolutely.
Yeah.
And a yay. And an air horn.
Also, I'm kind of like, I love this image here. He's the hugging face, and his face is in the hugging face emoji.
One day we're going to be as cool as other people, Cassie. Well, maybe me.
So this blog definitely has allowed me to pull it apart and figure out what's happening. Okay, so now we understand kind of the high level of what's happening. There's different schedulers. And remember, those are the ones that kind of go through and process different, I guess you could think of them as different transforms on the inputs and outputs from the model until we get a good image.
Oh, so it decides when it stops.
Yeah, so the scheduler steps, you decide how many scheduler steps you want to give it. So if I go to my C# program here, here's the number of denoising steps. And the number of steps decides how crisp the image is. The guidance scale, the higher the number, the more clear and detailed, but the less diverse of images you're going to get. I think of it kind of like a temperature.
I see.
So the 7.5 is what they recommend, 7.5 to 8 based on the blog. So that's what I've been playing around with. So the guidance is performed during the steps, which we'll see. And then the batch size is just the number of images that you want. So if we go back to our blog, you can kind of see we have the scheduler. It's saying, again, like a lot of the information that's from here, it's 50 steps. They said should give you a good image. You're always kind of playing with performance, right? How long am I willing to wait for the image? How can I get the best quality I want and get the results I want? So all those different like hyperparameters that you would do, in a non-multi model is the same thing. You have all these different parameters that you give it in order to get the result that you want, right?
Got it.
Okay. So this talks about, the text encoder and the tokenization, the scheduling, all the kind of different things that we already talked about, the UNet and the encoder to get our result. And then if you want to run it in Hugging Face, they have it here. The cool thing though is if you keep going down on this blog, they have broken apart each step in the pipeline.
Ooh.
Yeah. So you can do the nice wrapper and just use the one that exists, or you can come here and you can see how they broke it apart. So when I usually am taking something like this and I'm transforming it into C#, how I do that is I have the Python version running, and to make sure everything is the output that I expect, I will look at things like, is my tokenization the same? Is my size, my model, my tensor shapes the same? Am I getting the right tensor out? And that kind of helps me make sure that I'm doing things correctly. So when I'm transferring something that I already have in Python, I'm kind of doing this like back and forth between them. So that's one of the ways I reverse engineer and do these things.
So let me see about you. What you did is you went to the blog post, you put it all in a notebook and ran it and made sure it worked. And now you're saying, let's see this work in C#.
Right.
Got it. Okay, cool.
So let's go back to our C# code and take a look at the first thing we do. So I was using the same prompt as them, just for consistency, making sure my tokenization and my embeddings and everything else was coming out the same. Although since I have it running locally, I could change that and just check. I always do that sanity check to make sure that that's not an issue. If I go into my tokenized text here.
Is there a measure of is it stochastic in the sense that it's random? Like if you have a different random seed, it's going to produce something different? Do you know what I'm asking?
Yeah, no, the tokens are the same, because the tokens, I always think of them as like a dictionary or, if you are an enum, there's always one number that equates to one word.
What about further down the process? Like, is it going to produce exactly the same mangled astronaut hand guy on the horse? Or is there some randomness in there too?
So I believe the higher the guidance scale, the more consistent of image you'll get. There's also, when you create the static, you can provide a static input for the random, and then you always get the same random image. Okay. Or you can have a random go into your random creation, which is what I'm doing. So there are ways that I haven't tested this a bunch, but from what I understand, there are ways where you could get more of a consistent output if you wanted based on the different parameters. There's also different parameters that you can change for the scheduler, which will change how it denoises the
Okay,
image, from what I
cool.
understand. So there's
Sorry
a
about
lot of different pieces, and I don't know exactly what parameters you'd put in order to get, a pretty consistent image, but I do believe you can do that and play around with it and find, and if that's what you're looking for.
Got it. So you wrote a text processing to do the embeddings for you.
Yep. Which
Cool.
is just like any BERT model or CLIP model. This part isn't really anything different if you've done, those, a transformer.
It's just different because it's in C sharp.
Yeah, that is true.
Yeah.
Although I do have a BERT NLP C# implementation example that I created.
Oh,
So that
so
does exist.
okay. All right. All right. All right. Let's keep going.
Okay. So here is my ONNX model that has my clip tokenizer. So the cool thing about this on the BERT one that I did, there was an open source project that somebody created that had created the tokenization as a library that I could use in C#.
Oh,
That didn't exist for clip. So when I started this project, I was concerned that I'd have to write my own library to create a clip tokenizer. And thanks to the amazing ONNX Runtime team, they're like, "Oh no, we got you. Just use ONNX Runtime extensions." And I'm like,
ooh,
"Best,"
that
which
is
just came out,
nice.
by the way. I mean, it's been in GitHub, but it was just released. Some different packages. There's a lot of NLP tokenizers that you can grab and then use this in any language.
The
Mhm.
audience agrees. That is a great thing.
So to use ONNX runtime extensions, I have this DLL. So right now I had to, or at least when I started this project, I had to compile it locally and add my own DLL. That is not the case with the new version. So I could refactor this, I believe, and I would no longer need to have this DLL included. It would be part of the ONNX runtime package that you would download. But you do still need to register the op in your session options. So custom ops are a way to extend ONNX runtime for different scenarios, and it's how they implemented the ONNX runtime extensions package.
I see. Cool beans.
And so from there, I am going to send in my session options, create my inference session. If you've used ONNX runtime before, this should all look very similar. I have my model, I'm sending in my options, and I'm getting back my tokenization from my input string. So I return back my input IDs. This is another thing I need to look into. It's expecting the size of the tensor size of 177,768. So one of the things that I needed to do was pad based on this token. And again, I saw that from my testing here. I don't know if I can see. So you can see here, this is what the tokenization should look like. And this is why it's so helpful to go back and forth to make sure that my tokenization and my tensor shapes are the way that they're supposed to be.
Hold on, I don't understand. So, as you're passing in the text, I thought the embedding looked up a value in a dictionary for each word and pulled out a vector. Is that right?
Yes. So this, let me go back. This is the tokenization of the actual words. These are the indexes, I guess you could think of those words for the token, for each token. So this is the token. Oh, actually, it's up to here.
Yeah, because the other ones are like blank or something. Like 49407
Yep.
is like a space or something.
Yep, exactly. So those are the padding in order to get us to the tensor to the right shape that the input is expecting for our model.
I see. Does that mean that the model is expecting a sentence no longer than 77 words?
Yeah,
Okay,
I believe so.
cool. Okay, that makes sense.
So if we go back here, I had to add that padding in order to make sure that we got the right shape.
And the 768 is the size of the embedding, right?
Yep.
Okay, cool. Okay, I'm following you. I'm in the game now, friends.
And I'll do my best to answer your questions accurately. So the
I mean,
next
you just
piece,
learned this like the other day, right? You're like, I'm sitting here with like
yeah.
10 years of college, and you're like, I learned this the other day.
I would say it started like maybe 3 weeks ago on this project.
Oh, only three. Three. It took her 3 weeks, and I went to college for 10 years. Great. Help me out. Help a brother out. This is great.
Okay, so then once we get our tokenized input, we're going to send that in to get our encoding. This is the encoding model in my here that is actually provided from the Hugging Face model that you're download. So this one is one that I have from our extensions, and this is the one that you would get if you went to Hugging Face and downloaded the model.
So you're effectively downloading all the models, and you're in tandem running them. Okay. This is all right. We're starting to rubber is hitting roads right now. This is great.
Okay, good. So then from there, we are taking the input IDs and creating our input tensor and running our encoded session, which is just our inference session for the text encoder model, and getting our, it actually comes back with 3 different things. It comes with the last hidden state, the pooler output, and, or no, maybe it's just 2. But so far, I've only seen that the last hidden state is what is used. So that's like the checkpoint, from what I understand. I don't know if I'm going to explain that right, but I think it's the checkpoint from the model that would be the embedded result of that input. Did I say that right? I'm not sure if I said that right.
So let me see. So this, can you open the model, the embedding model? Let's take a look at that one in Netron. Hold on. Netron, the tool that all software developers use to look at ONNX models. Get yours today for free on GitHub and other fine retailer locations. Netron. Models for you and me. And that was so good. Like, I want to use Netron now. We are using it. Look at that.
It takes a minute to open because
that's why I was buying you time. I knew it was going to take a while. That's why I was like, let me do the thing here.
Okay. So here's our inputs and outputs.
What's that side thing that it's got going on?
Oh, this is large. I think I can let's make this smaller. Maybe it's big. So I usually keep it zoomed in because I've been looking at.
What is this model? This model is, I thought this model was the embedding model.
This is the clip embedding.
Okay.
Yep.
Okay. So it's basically learned a thing so that the output of it is the vector of that word in whatever image latent space it decided to use.
Yes, I believe so.
Okay, cool beans. That makes sense.
All right, so we get our last hidden state from the embedding, and then we have to fill our tensor with the result. So we need to create ONNX Runtime tensors, and we need to fill it both, vertically and horizontally by the result of the inference.
I see. So you're squaring up this hidden state into like some kind of input tensor.
Exactly.
Got it. Okay. Exactly. Cool beans. This is where my coding, this is where like I start to suck at this stuff, because it's like, what? It's not the right size. And everyone's always failing on like, you're missing the first dimension. It's like, oh, I don't want to do that.
Yeah.
So good for you. I suck at this part.
That line of code, I mean, it took me a minute to get it right. There's definitely lots of time that has gone into this so far. But one of the things I like to do in order to understand things is I need to pull them apart and play with them. And that's kind of how I learn and understand. So it's been really enlightening. But there's still obviously things I don't know, like you were asking about. Okay.
Well, your effort is our gain. Thank you for that.
So
all right,
fun.
Let's keep going.
Okay. So next we are going to go to the inference. So now I have my number of inference steps. I have my text embedding. I have the guidance scale. I have my batch size, which I'm only asking for 1 image, and then the height and width. So the height and width, the kind of default for Stable Diffusion is 512 by 512. It has to be a multiple of 8, from what I've understood.
Mm-hmm.
So
here's my question. I thought the UNet only did a 64 by 64, or is this like a help me out with this?
Yeah, it does do 60 by 64. So we divide by 8, and then we bring it back up after the result. So when we rebuild it at a larger scale. So we set it as like the ultimate height and width that we want. But yeah, it is 64 by 64 that goes into the UNet model.
I see. So is this the UNet, like the middle thing before the decoder?
Yeah, so if you go back, the UNet is where the inference, so you have your scheduler that denoises, and then you go through the UNet. So if we go back up here, if you remember that loop on the side, let's go back up. Wait, where did it go?
Come on, picture. Don't let us down.
I realized that after this that I'm such a visual learner because I saw this at first and I wasn't sure. And then as I started pulling it apart, I came back to this and I'm like, oh, this explains pretty much everything. So you can see we've done these two pieces, right? Our
Right.
tokenization, our text embedding. I haven't showed you this part yet. That's one of the other inputs that we'll get to next. But then this is our model that does inferencing. And then we go through the number of steps that we want to denoise until we get the image that we
But
want.
you're passing in like 512 by 512. I thought it was a 64 by 64. Why are you? That's what I was confused about.
Yeah, I divide by 8 in order to get 64 by 64. But the output image that I want is 512 by 512.
I see. Okay.
Okay. So then that's where we're at in this whole process. Now we need to create our randomized image, right? Our static. So here I'm getting, this is the model. This is the scheduler and the time steps. This piece I'll get into last because that's where I'm still debugging things and making sure they're correct.
Right.
From here, I'm creating a random seed. And then from there, I am generating a random image in the right size. So I'm getting the latents, which is the input. So batch size is 1 image, 4 channels, 64 by 64. And then from there, I'm filling this tensor with random.
Oh, Cassie, this is where I wish C# had like a set this range, like the range stuff in Python makes it so you can set things in such a glory. Like this could be like a single vector operation in Python, but not in C#. I've asked them to add stuff like that for me, but
I wish they would. I have to say these pieces of the tensor looping through and filling the tensor, there's probably maybe more performant ways to do it. I don't know, but that part is I think one of the more difficult parts because in Python it's so simple to create a random tensor.
And it's simple to vectorize it too. Vectorizing is where you get all the juice, and this is just like 4N runtime.
Exactly. And so what is created?
End of the fourth. Sorry.
Do I have an image? Oh no, I'll have to. Oh, here. This is it. This is the image. So this is the image that's created from that. This is our noise.
Yeah, it was just a TV noise.
Yep, exactly. You can hear it. You listen closely.
That's not me at all.
That's the magic of AI.
Don't look at my mouth.
Oh, that was great. Okay.
Oh my goodness.
So we have our TV noise.
So good.
And then from there, I'm setting up using CUDA. So I want to use the CUDA execution provider in my inference. So that's part of the session options that I'll need to send in while I'm doing my my UNet inference. So
how do you know like what things, like those strings are very stringy? How do you know, like how did you know that those were the strings to put in there?
It's in our docs.
Oh, okay.
But you don't necessarily need all of these. These are default values. I just include them in my samples so that people know they're there.
Ah, see?
I could copy all those out. Those are all the defaults. You don't have to. I guess that's a discerning because even the device ID. So I could copy. Right. I could comment all this out and just let it know that I want to use the CUDA execution provider and add it as the option. I put these in case I want to mess with the defaults, and then I don't have to go think about what they are.
And which GPU do you have?
I have a 3070.
The only reason I ask is because I just bought a new one, and I wanted to mention it on the show.
Which one do you have?
That's a great question, Cassie. I just got a 4080. Pooh!
So
I drove all the way to Best Buy to pick. I had to buy it, and they're like, "You have to come get this." And so I showed up, and I had it came in a huge box. I installed it with Glee, and now Minecraft works 2 times faster. It's glorious.
Have you tried VR Minecraft? I bet it would run really well on your.
I have not got into VR because 1, I'm old, and 2, I'm old and would probably get dizzy.
So the VR one for Minecraft, the one thing you can't do, a lot of that has to do with the frame rate update that makes you feel dizzy or nauseous. That's what a lot of people feel like when they have that issue is they need better quality is usually, or if they're just super sensitive. But with Minecraft, the one thing I found you can't do in VR, for me at least, is that if you try to, you know how you can fly and then double spacebar and drop down?
Yes.
If you do that in VR, you're not gonna feel good.
Ooh, because it's like you're falling and your brain's like, ah, and your body's
Yeah,
like, no, but wait, ah.
and I
Hold
feel
on, I
like
have a sound effect.
the refresh rate makes your eyes really tired for something moving that fast. So a lot of that has to do with like the movement versus your not movement versus your brain. Like it's all of those things come together. So I think a lot of it comes down to also VR game, like the design of the game. Some games that are designed really well, you should not feel that. And if you have a decent system with, um, you know, or if the game was made to take advantage of the hardware in the way that it needs to. I think a lot of people had a bad experience with VR back when we really didn't have the power to run good experiences. And then they're just like, no, that makes me feel sick.
Oof. By the way, that scream you heard, the Wilhelm scream. It's almost in every movie. Like if someone dies, like they put it in movies because I think it's a thing now. Like the first Stormtrooper, Indiana Jones. You know, someone falls off a roof.
Mm-hmm.
You know, that's the Will. You've heard it in movies, right? It's the Wilhelm scream.
Yeah.
All right, let's keep going.
Okay.
We're gonna run out of time, man. We're so chatty here.
We are, but that's okay. That just means that we'll have to come back to it
I
at
love
some
it.
point when it's working all the way.
Mhm.
So in the inference step here, we send in the text embeddings, the latents that we created, and our time step. And so this is the loop of the time step that will go through and inference through, oh, sorry, this was the model input. I said that wrong. Where's my model inference? It's down here. Here, where my breakpoint is. So here I'm creating the model input. I should jump there quick for the results. So the ONNX runtime is expecting a list of named ONNX values, and I'm creating those from the tensors with the labels that are expected as the input for the model.
Got it.
So if I go back, now then we run inference here. And then I get the output, which is, again, the size of 1, 4, 64, 64. Those are my output latents or my noise prediction.
And for each one of these, it's going to get better and better, right?
Yeah. Yep. The scheduler does the denoising from what I understand. The UNet model is part of that process, but I don't think I fully have like grasped that in a way to explain it well.
Because I thought this like, the scheduler to me was like, it seems like it's just a for loop, but you're saying the scheduler does some machine learning in there too?
This is the scheduler, and it does a lot of math. Seth, excited. What was you were gonna say? What was the thing you were gonna do every time I said math?
I almost failed this. I almost.
Can I give you another chance? You want to try again?
Yes, I'm ready. Finger
Okay.
is ready.
The scheduler has lots of math. There we go. Yeah.
Thank you. Okay.
And
What
so
is? Let's see this here.
this is the part that I'm still debugging around the denoising process. So, and that I'm still grasping. So I'm not going to explain that.
What's LMS stand for? That sounds familiar to me. LMS.
Let me pull up the scheduler. So this is the wait, that's not the right one. Where's my Python one?
Python.
Oh, it's on the other screen. There it is.
There you go.
So this is the one that's from linear multi-step scheduler for discrete beta schedules. That's what this does.
Original K diffusion implementation by Catherine Krausen. A boss. Looks like it has some mix-ins. Great. Scroll down, please. No, I'm trying to look at the comments here.
Oh, okay.
Number of diffusion steps used to train the model. So diffusion steps is something that you're trained the model. Like, is it a hyperparameter or something?
Mm-hmm. I believe so, yeah. For training. I haven't trained one of these. So that's for the train steps. We're going to give it the inference steps.
Interesting. Option to pass an array of betas. What the heck are the betas? I feel like I want to read the paper. Image.
Yeah.
Oh, prediction time. Go ahead. Go ahead. Sorry. What have you
Well, and
found
I was
so
just
far?
going to say there's multiple different schedulers. And I should pull up the doc that shows you the different, so diffusers, scheduler. I can't type. There we go.
Scheduler.
Oh, I wonder what Bing's going to tell us about this. Now I'm like,
Bingus. Bingus.
what are types of noise schedules? See if this gets it. And while it thinks about that, noise schedule diffusion models. Okay. So cool. We're having AI explain AI to us so that we can do more AI. Like, this is
I know. It's like we just are like in the third level of dream state here.
Is this reality? We live in the future.
Goodness. A noise schedule is a function that defines how much noise is added to an image at each step. I thought you wanted to remove noise.
Yeah, so let's look at the, how do I go to the, I want to look at the, this one.
Okay.
My understanding was that it was denoising, but maybe the model denoises and the scheduler adds noise strategically. Maybe I have that part wrong. Like I said, this is the part that usually when I come on here and I have something that I've worked on, I've worked through all this stuff. So this is the
So we're
piece
still,
I'm
but
putting
the
together.
thing is Cassie, we are almost out of time, and so
Oh no.
go figure. Like, we might have to come back and do this part again because the denoising, like, my understanding is that the scheduler step goes to denoising process, but it looks like it's noiserating. I just made that word up. The other way. So maybe because my sense is that these things, they have a forward pass and a backward pass when they're optimizing.
Let me see something. So theory of the scheduling algorithm functions out of scope of this notebook. Let's see.
If we do not have 800 tabs open by the end of this, we have not done our job.
Did we even code if there's not 800 tabs?
I know. Elucidating the design space of diffusion-based generative models. See, like, this is the kind of stuff that if you use in sentences makes people think like we're super smart. What were you doing the other day, Cassie? Well, I was elucidating the design space of diffusion-based generative models. Oh, good gravy. And with that, I think we're about out of time. Can you in the last maybe 3 minutes, because that's how much time I think we have. What are our next steps so that we can revisit this again?
Yeah, so I need to finish building out the scheduler. And then from there, once we have that piece, we're able to loop through and we would create the final output, which would go to our decoder, which would create our image. And then from there in the decoder here, we would then convert our image to, or convert our tensor into an image. And so I can show you what it looks like. Here's my test layer. So here's after one.
Ooh.
Yeah, it kind of looks like space, right? If you like,
yeah,
in
if
an
you
abstract.
squint and maybe even close your eyes a little bit,
Yeah,
you can imagine. But this is just one step through the
this is
thing.
one step.
That's cool though. That like in one step, it's already starting to undo stuff. That's
right.
crazy.
So we need to add 50 steps, and then the scheduler, once the schedule works correctly, then we'll be able to loop through that, and then we should have our output. So I mean, the majority of this has been put together, and yeah, I'll have to come back once I have the full thing working. And cleaned up, the rules. First, you make it work, and then you make it pretty. Right now, I'm just on the make it work right now. It's definitely not pretty.
Yeah, my mantra is always make it work, and then make it right.
Yeah.
No amount of pre-optimization is going to get it out the door faster. So, for those wondering where this is, you can go. Boom.
Yep. And there's even sample notebooks in here. You can play with it in Python, whatever language you want. Well, not actually. If you want to play with it in other languages, you got to build it yourself right now. So if you want to play with it without building it yourself, Python is the way to go. And the diffusers library has so many different pieces of it. Like I said, there's the ONNX Runtime pipeline within it, so you can run it in Python with ONNX Runtime. You can use GPU. You can play with different schedulers and see the different outputs. I found that Hugging Face has another blog just on schedulers. I couldn't find it right. I should have had it ready, but it shows the differences in the images based on the scheduler that you choose, and it's really cool to see how you. That's another way where you were asking earlier how you can change the output, or see
Amazing.
how you can get more consistent, that type of things.
Well, this is cool. Thank you so much for spending some time with us, Cassie, and
Yeah.
showing us the deeds. You're also a host. What do you want to say, like as a host?
Build cool stuff. Hang out with us more. I don't know.
Yes, thank you so much for watching, and hopefully we'll see you next time on the next episode
Thanks,
of
Seth.
the AI show. Have a good break. We'll see you on the next one.